Next up, we will move ahead and understand what is central limit theorem. It is one of the important or the fundamental concept in statistics. It describes the behavior of the sampling distribution of the mean. We already discussed about what is sampling distribution is all about. Okay, in the case of central limit theorem, what it tells us, irrespective of the shape of the distribution. Look here, in this case, we have four different distributions, four different population. In this population, the distribution pattern is something like this. It's a normal distribution. This is a uniform distribution. The skewed distribution, random distribution. So what it says is the central limit theorem. As the sample size increases, it approaches a normal distribution with the mean nearly equal to your population mean and standard deviation equal to the population standard deviation divided by square root of n. The n is nothing but the sample size. So irrespective of the shape of the distribution, the sampling distribution of the sample means approaches a normal distribution as the sample size gets larger. So this one I demonstrated as part of sampling distribution itself. Look here, in this case, look here, this is what the sampling distribution in the, look here, in this case, these are the, the 6 samples we took it initially. And then when I plotted this in a chart, so we could see that the distribution of these samples, 6 samples, means we can see it here. So the distribution pattern is not precisely the normal distribution. But when I increase the sample size, the number of samples, as I increase the number of samples, you can see the sample distribution comes approximately normally distribution, right? So the sampling distribution of the sample means, these are the sampling distribution of the sample means, approaches a normal distribution as the sample size gets larger. See, in fact, the sample size is in this case 2. So when you draw more samples in each sample, right? If the sample size is somewhat closer to 30, it will become approximately normal. Even in this case, the number of samples also increases. As the number of samples increases, it becomes approximately normal. So in the case of sampling distribution, in the case of central limit theorem, the sampling distribution of the sample means, the sampling distribution, these are the means for different samples. If you plot these means in the chart, that is nothing but your sampling distribution. Okay, so when it approaches a normal distribution as the sample size gets larger, that is what the central limit theorem tells us. In this case, remember that irrespective of the population shape, as you increase the sample size, it becomes normally distributed, especially when the sample size is 30. This is the one you need to remember. If the sample size is 30, it is becoming approximately normally distributed. Okay, so now the question is, why central limit theorem? What is so big deal about central limit theorem? Before we proceed, this is the one we discussed already, right? The sampling distribution mean is equivalent to your population mean. This is what we discussed. This is my population mean. This is my sampling distribution mean. We can use this notation. Mu x bar is nothing but the sampling distribution mean. This one. And this is your population mean. Mu. Okay. So in this case, mu is equivalent to mu x bar. In this case, the mu is 2.5. The population mean is 2.5. Mu x bar is 2.5. The sampling distribution mean is equal to the population mean. That is also one of the rule conditions in sampling distribution. Apart from this, the standard deviation is equal to the sampling distribution standard deviation is equivalent to the population standard deviation divided by the square root of n, which is nothing but sample size. So this is what is the population standard deviation? In this case, the population standard is sigma. Sigma is this one, and in this case, this one is sigma. Listen, this is not. Let's see. This is sampling. Yeah, sigma. Listen, yes, sigma, yes, something like that. Okay. Sigma is equivalent to sigma yes here. Sigma v sigma yes divided by. Sorry, here the sigma. So in this case, sigma s equal to sigma divided by square root of n. The n is nothing but the sample size. So like how the population standard deviation is equivalent to the sampling distribution's mean. The population mean is equivalent to the sampling distribution mean. All right, is same. Similarly, the sampling distribution standard deviation is equivalent to the population standard deviation divided by square root of sample size. So in this case, the the population standard deviation square root of n is this one. This value is approximately equivalent to the sampling distribution standard deviation. So the calculated value of the sampling distribution standard deviation is very close to the theoretical value, this one. Hence, it meets the central limit theorem rules, right? The conditions. Now the question is, why should I use central limit theorem? How it is helpful. Remember that we cannot create practically a sampling sampling distribution in real world scenario, because in the population you will have huge volume of data. Okay, it requires a huge effort. We cannot afford to take multiple samples to create sampling distribution, everything. Okay, so in that kind of situation, the next question is there any way if I can take a single sample to make inference about the population? Is there any tool that is available? That is where you have something called confidence interval and hypothesis testing comes into picture. In that kind of situation, we can apply the central limit theorem. For these two, confidence interval estimation and hypothesis testing, the engine driving these two concepts like confidence interval and hypothesis testing is nothing but the central limit theorem. Okay, so with the combination of central limit theorem, confidence interval estimation, and hypothesis testing, we can use a single sample to make an inference about the population. To summarize, as part of central limit theorem, we have understood as the sample size increases, the distribution of the sample means the sampling distribution sample means approaches a normal distribution with a mean nearly equal to population mean, and the sampling distribution standard deviation is equivalent to your population standard deviation by square root of n. This one we already discussed in central limit. Sorry, the sampling distribution also, right? So in fact, those what we discussed there, or like your, those are like your central limit theorem only. Okay. Remember that as the sample size increases, especially when the sample size is equal to 30, the sampling distribution of a sample means approaches a normal distribution. Rule number 1. Rule number 2, the sample distribution mean is equal to your population mean. And the rule number 3 is the sampling distribution standard deviation is equivalent to your population standard deviation divided by the square root of the sample size. That's it.